So let's welcome our last speaker, Dhruv Batra from Georgia Tech. And he is an associate professor at Georgia Tech and a research scientist at Facebook AI Research. I think his work is famous for his work focuses on the intersection between language and vision. And yeah, let's welcome Professor Dhruv Batra for his work on embodied AI. Yeah.
Okay. Thank you. Thank you for having me and thank you for organizing this. I hope people can see the slides on the screen. Yes? Okay. So what I want to talk to you all today is about Habitat 2.0. It's a next version of a project that we've been working on for a few years. And it's really a journey from 2018 or so since we started working on Habitat 1.0, and that was published at ICCV in 2019. And since then, we haven't stopped. We've been working on this for the last 2 years, and we've been making this transition from navigation to mobile manipulation. And that's what I want to tell you about today. I want to quickly recap for those who may not be familiar. So Habitat 1.0 was a paper that was published at ICV 19. We were studying navigation research problems. So it's a simulator where we can load in 3D scans, insert robots, render egocentric observations, and train for navigation problems. Our sort of main scientific understanding in this field was work by Eric Wymans, who showed in a iClear paper in 2020 that point goal navigation in the presence of ego motion sensing is an entirely learnable problem. You don't need any model, you don't need mapping, you don't need planning, just egocentric observations. You can, on the y-axis is success in new environments, on the x-axis is amount of training. And again, this is test success. And so you can get near perfect results if you scale it out to 2.5 billion frames of experience. And that was surprising. And we've since then also shown that zero-shot sim to real transfer essentially works. You can train a policy in simulation, you can deploy it on a robot in a real environment, and it works to a reasonable degree. Not just that, there is high sim versus real correlation. So you can take multiple models, you can on the x-axis plot the performance in simulation, on the y-axis you can plot the performance on a real hardware in a real room, and you get strong correlation between the two, which suggests that you can use this for model development. When you pick a model in simulation, you have some degree of confidence that you are making progress in the real world. And there has been an annual competition that we've been organizing at CVPR for the last 3 years on point goal navigation in the absence of ego motion sensing. So you have to do visual odometry and more semantic tasks like object goal navigation. There's been an interesting development of a community here, more and more teams participating. And what we also see correspondingly is that the state of the art in point nav without any sort of ego motion sensing has also tremendously improved. It started off at like 15% success in 2019, and this year the challenge winners have essentially saturated this data set as well. And we're seeing not quite the same, but still consistent progress in object nav. And I encourage you to check this workshop out tomorrow. There's multiple challenges being organized. So that was Habitat 1.0. As I said, it was entirely focused on navigation. And for the last 2 years, we've been working on this transition to mobile manipulation. What we want to do is develop systems like these. So this is a mobile manipulator, fetch robot. It can navigate, it can interact with objects in the scene, it can open drawers, pick up objects, and then take them from one point to another. So these are the sort of home assistive tasks that we'd like to train our virtual robots to be able to do. And this robot will go back, close that drawer, and continue the rest of the process. So how do we get there? This is work by a large set of people. A significant percentage of them are either at Georgia Tech or at Facebook AI Research, but there are people at Simon Fraser University and others at Intel. So how do we get there? What do we need in order to get there? We tend to think of this entire problem in a 3-layer stack of 3D assets, simulator capabilities, and task. How do you define the task and how do you study systematic evaluation? So let me tell you about exactly what task we are studying. This is something that we call the home assistant benchmark. How do we train robots to serve as home assistants. The simplest setting is just things that the RL community and the robotics community already studies today, which is just a pick task. You have a fetch robot, consists of a 7-degree of freedom arm. You have onboard sensors. So you get a head camera. We also experiment with an arm-mounted camera. There are ego motion sensors for the base, but in the pick task, you don't need to move your base. You have joint sensing on the arm, and you just have to reach out and pick an object up. The object is specified by the center of mass of the object. You have to train a policy that can do this. The sort of problems, as with the sort of key requirements, as with the navigation problem, is no pre-built map, no assumptions of the environment. You don't get to know what objects, no 3D models. This is a new environment, new object. You have to you just have to operate from onboard sensing. You cannot assume anything about this environment. And I already, this is the simplest setting. I will generalize the tasks a bit, but already you can see that this is much richer visually compared to the other environments that you might see in the RL community, for example. The OpenAI Gym fetch reacher tasks, or the kitchen, the Franca ARM kitchen tasks that's used in some of the relay policy learning work. Those papers tend to, first of all, not even have a house. There's no environment. There's nowhere that the robot can go, and they tend to not be very photorealistic. The kinds of tasks that we study are actually more sophisticated than just picking up an object. So this is a task called tidy the house, which means move 5 objects from their start to goal location. So this robot has to navigate, pick up object number 1, navigate to the goal position, and put object down at the goal position. So there's just 5 multi-goal navigation pick place tasks. There's a prepare groceries task where you have to pick an object up from inside the refrigerator, put it on a table, and pick another object and put it inside a container, right? So these containers are tight spaces where the arm has to get in. There is the set table task where the container actually is closed now. So the robot has to open the drawer, pick up an object. There's another container, which is the refrigerator, which also has to be opened. The object has to be picked up. These are tight navigation manipulation spaces. And then those containers have to be closed again. And the goal specification that we're working with is something called the geometric goal specification. So you do not get names of objects. The robot, in its starting coordinate system, in the robot coordinate system, it gets the start positions of where the object is, the center of mass coordinate of every object that is the object of interest, and its final destination center of mass coordinates. The pose of the object does not matter. The shape does not matter. Those information is not provided. The only thing that you provided is center of mass of a list of objects at start and at end. And you do not have a map of the environment. You do not know where obstacles are. You do not know what surfaces these objects are resting on. You just know center of mass. And this can be somewhat challenging because an object can be contained inside other objects, right? If there's an apple inside the refrigerator, the center of mass cannot be reached directly because there is a container that has to be opened. And so those things have to be sensed by the robot. One object is inside the bowl is inside the drawer here, and the apple is inside the refrigerator. And so these containers have to be opened. And the final coordinate system of the target may actually have dependencies. So the center of mass of where I want the apple to be is resting on top of the bowl, and so you cannot put the apple first. It will not stay there. It will just fall down. So the robot has to reason about the task order as well. We follow recommendations from a tech report that some of us had put out last year. This is a collaborative effort between a large group of people as well. And what we essentially wrote down in that tech report was a generalized rigid body rearrangement problem. We wrote down rearrangement as studied in a lot of different mobile manipulation problems and static-based manipulation problems by the robotics community and computer vision community as a generalized rearrangement problems to go from S0 to S star with different goal specifications. Some of the assumptions that we laid out as assumptions that I think are a good starting point for the research community is to start with just piecewise rigid bodies, like forget deformable objects, forget fluids, clothing, everything else, and to very clearly write down that the robot should not have access to world state. No pre-computed maps, no knowledge of 3D models, no logical state abstractions, no magical sensing of physical parameters. You don't get to know how heavy something is. You don't get to know kinematic chains of articulated objects. You just have to sense everything from onboard sensing. What is out of scope, as I mentioned, is non-rigid dynamics. What is also out of scope is non-physical, physical transformations, like no welding, sticking of objects, no cutting, none of that. And so the world is piecewise rigid bodies. And one of the things that we laid out in that tech report, that since the state is not visible to the robot, you have to specify goal in some way as a function of the state. And so we wrote down in that tech report some goal specifications. It could be geometric goal specification, as I've already described, center of mass coordinates of objects, or it could be a language goal specification. So you could say, you know, move the toaster next to the coffee maker. That's an instruction. Or it could be an image goal specification. I could show you the final picture that I want the environment to be in, or it could be some other goal specification as well. And we describe in the tech report things like, you know, there are challenges of perception here. You have to, of course, do state estimation. What are the obstacles in the world? What are the containment relationships in the world? Navigation is a problem here because you'll have to move to get to those objects. Manipulation is a problem, although we emphasize that the kinds of manipulation that we're focusing on are gross motor control problems, not fine-grained motor control problems. And the distinction is it's about trying to move arms and bodies and not about fingers and dexterous manipulation of small objects. One of the reasons why we delineate that border is because we believe that both in simulation and in hardware, the technology may not be mature enough to take on those problems. Because if you want to deal with dexterous manipulation with fingers, you have to have extremely sophisticated simulation software to model contact dynamics and deformable objects. Okay, so let me tell you where some of these 3D assets come from now that I've described the task. In most of our navigation literature, we were studying these problems on scans of indoor 3D environments. This is a scan from a data set called the Replica Dataset. This is one of the highest quality 3D reconstruction that you can get. This renders out images that are not 100% indistinguishable, but fairly accurate compared to realistic images. But one of the problems with scans is that they are not interactive. The refrigerator is sort of baked into the environment. You cannot open the door of the refrigerator. And so in order to take on this task, we recreate Replica as Replica CAD. So we hired artists who went in and looked at these assets and recreated them as CAD models, interactive CAD models. What that means is essentially that the entire house, every single object, every chair, every table, every lamp, every book, every object in this physical space has been recreated as individual pieces of CAD models with physical properties, masses, with articulations. So if a drawer can open, then you have to annotate the hinge joint of the drawer and other aspects of this. We also create macro variations. So the same furniture can move around so that you can study systematic generalization. So it's the same assets, but variations of the spaces. And of course, micro variations where some of the small things will move around, but the entire house layout will not change. So this lets us create multiple environments from the same underlying 3D assets. We have a pipeline to do procedural generation of clutter. So we can insert objects on top of annotated surfaces. Surfaces of supporting surfaces and containment relationships have been annotated. Therefore, we can do programmatic generation. And what this means is you can train under a large number of settings of different objects and different receptacles that those objects rest on. And you can do systematic evaluation, systematic generalization to picking up or interaction with new objects. So this object has never been seen before in training, or to new receptacles. So the robot has never picked any object from the sofa in training, and it's being tested on that. or to systematic generalization to new layouts. So in training, the house looks like on the left, the same table appears as in testing environments, but it was not in this part of the house. The house has just been rearranged fairly significantly. And so this is the weakest form of generalization to new layouts. Okay, so in terms of what sort of capabilities the simulator has, I've been showing you that throughout this talk, but in some sense, the key problem that we had to solve was rigid body physics. We did this through integration to the Bullet physics engine. So we can obviously simulate forces, gravity, picking up objects, mobile manipulation, and so on. But also one thing that we solve is we can run the simulator on a browser so that we can actually connect it to Amazon Mechanical Turk and have people play the role of the mobile robot and pick up objects on the web. In terms of how fast this is, we measure speed in steps of simulation time. So each step of simulation consists of rendering 2 RGBD images of resolution 128 by 128, which is what is fed into our model, and simulating rigid body physics for 1/30th of a second in chunks of 4 1/20th of a second. The reason why these numbers have been chosen is because 120 hertz control is pretty common in the controls literature, and 30 hertz rendering is pretty common in the rendering literature. And so what the setting of these numbers do is it basically sets 30 steps per wall clock second as real time. Your cameras are rendering at 30 hertz, and physics is simulating for 1/30th of a second. So 30 steps per second would be real time. And so that's what we'll compare our performance to. We compare to other simulators that are widely used. So RL Bench is a simulator that uses a fixed base arm and a tabletop setting. And it's roughly in the 50 steps per second range. AI2Thor is a widely used home scale room scale simulator, which is built off of Unity, and that runs on the 60 steps per second range. iGibson is a project out of Stanford, which also uses the Fetch robot, amongst others. And that's according to their paper, is 100 steps per second. 3D World is a simulator from MIT and IBM, which is in the 170 steps per second range, according to their benchmarks. Sapien is an effort out of UCSD, and their range is between 200 and 400 steps per second, depending on the kind of rendering that's done. Habitat 2.0 single threaded is 1400 steps per second, which is over 3x faster than anything else available, and 47x real time, which means you can, if you want to simulate 1 minute of an experience of a robot, you can do that in 1/40th of a minute, 1/47th of a minute. But of course, because we own the software stack, we can run multiple instances on a single GPU, and we can actually even tune how the physics operates on the CPU versus the rendering operates on the GPU. And on a single GPU, Habitat 2.0 runs at upwards of 8,000 steps per second, which is 30x faster than anything else, and 280x real time. And of course, we can also show scaling to an 8 GPU node, in which case it runs at over 25,000 steps per second, and you can get to 850x real time. These speedups directly translate to how fast your experiments can run, because if you want to run training to hundreds of millions or billions of steps of experience, it is important that you cut out the 1,000 order factors in your training time. Okay, so that's the entire stack. In terms of the scientific takeaways of what did we learn? Well, we compared 2 different kinds of approaches. One is sort of the monolithic neural network type models trained with reinforcement learning. And what these models essentially do is similar to the navigation literature. They just take all sorts of visual observations, the RGBD frames. They encode them with classical CNN type encoders. There are, other state encodings, the robot state, the mobile base, the ARM configuration, and you essentially concatenate all of that, feed into an LSTM, and make predictions from a value head and an actor head. And the actor head is doing linear and angular velocity to control the base, and it's doing end effector displacement to control the arm. We are abstracting away grasping. So we are not controlling the parallel jaw gripper. We are essentially calling a discrete action to do the grasping when the end effector is close enough to the object. We also compare to classical sense plan act pipelines in the robotics literature. So the sensing is done via a 3D point cloud that is constructed from the head-mounted camera. The point cloud is treated as obstacles. And so a planning, an RRT style planner is run in the joint arm joint space to plan a path from the current configuration to the goal configuration. And then of course, a PD controller is used to execute that path on the actual robot. And this is combined with task planning so that you know whether right now you want to navigate, pick up an object, close a drawer, open a drawer, and so on. So you can either do RL alone, you can do sense plan act alone, or you can combine them with task planner. So you can make it a hierarchical approach. And in some sense, what we find is that as I mentioned, we are doing large-scale training on lots of different environments, and we are doing systematic generalization to new objects, new receptacles, and new layouts. And in just the pick task, I will just focus on that to give you a sense for numbers. We compare, and we actually have a couple of different takeaways. I ignored the numbers, but I think the takeaways are, if you only test generalization to unseen layouts, so I'm not even going to talk about the scene stuff, because there, of course, learning-based methods will win. It's not about the training performance, it's about held out performance. On unseen layouts, learning-based methods just like significantly outperform sense plan act pipelines. However, as soon as you go to unseen objects, they're getting very close. The error bars start to overlap. But once you go to unseen receptacles, sense plan act pipelines are actually much more robust. Unknown receptacles are really hard for learning-based methods, because if there is a small number of receptacles and some of the receptacles require entering into tight spaces, and so there isn't much experience. And so the learning-based methods aren't generalizing very well to those. In terms of the full tasks that I mentioned, the tidy house, by the way, which requires navigation, picking an object, navigation, placing an object, navigation, picking up an object, and so on. So this is the entire set of subtasks that are part of the tidying the house. We actually show performance. So there's success rate on the y-axis, and on the x-axis are these sorts of interactions. And we actually find that very few methods. So on this plot, you should think of this as an analog to a precision recall curve, right? So top right is where you want to live. Monolithic methods, RL methods, just basically don't perform this task very well. They're at 0% success very quickly. They can navigate, they can maybe pick an object up, but when you have to place it, it's basically zero after that. This is the kinds of policies that monolithic RL methods learn. They are controlling both the base and the arm, and it just leads to just wild behavior in simulation. This is a hard problem, because even designing reward functions that deal with multiple stages of this task is very hard. However, if you combine RL methods with task planning methods that have a notion for a pick skill, a navigate skill, a place skill, then they perform much better. So this is an actual result from a task planner combined with a set of skills, picking skill, navigation skill. So I'm actually not showing the skill boundaries in the video, but anytime that the robot is navigating, it is using the navigation skill, then it comes to rest. And when the arm is moving, it's either a pick skill or a place skill that's being called. And those are working much better. Of course, this is the curve. This is the curve for that method, and you see that it starts out fairly high at 80% initially in the first object it has to pick, but things start failing as it runs longer and longer. So overall, I'll say that our key takeaways were that flat policies really struggle compared to hierarchical policies. These are hard, long horizon, egocentric perception problems. Hierarchical methods incidentally suffer from handoff problems. What we see a lot is that you will call a hierarchical method, and what will happen is that the navigation system will go stop too close to the drawer, and the opening of the drawer will get blocked because the robot is too close to it. And the sense plan act pipelines are fairly brittle compared to our methods. So those are the key takeaways from this work. I'll stop here, and I'm happy to answer any questions that might be.
Yeah, thank you for a nice talk. So there's a question in the chat box from Mike Roberts. So he's asking, this is a really exciting work, and when comparing frame times across simulators like AI2 Tor, etc., are these other simulators also outputting image size of 2 times 128 times 128? So what is your intuition for why Habitat 2.0 renders so much faster than these other simulators? What is the low-hanging fruit that these other simulators aren't leveraging?
Yeah, thank you. I think that's an excellent question. So I should caveat that doing speed comparisons across simulators is first of all fraught with problems because they are not loading identical assets. They do not have identical capabilities. Sorry, I'm just trying to get here. They do not have identical capabilities on rendering or on physics end. My understanding to your precise question is no, everyone is not controlling on 128 by 128. In some of these cases, we reached out to the authors. So on the Sapien team and the iGibson team and RL Bench team, we reach out to the authors and we ask them questions. In some of those cases, we did not reach out. We just took numbers that were reported. My sense is that not every simulator does get proportionately faster as you restrict the pixel resolution. It's because the bottleneck is not ray tracing, for example, where there's a linear dependency in the pixels. So you reduce the pixels and you get faster speeds. My sense is that a lot of these simulators are bottlenecked by different things. In Thor's case, I suspect that it's a binary. They actually cannot go in and make Unity faster, even if they decide to render low resolution images. In other cases, in Sapien's case, my understanding from talking to them is that their physics runs much faster. They can run at thousands of steps per second in the physics time, but it's the rendering that they feel is bottlenecked and the CPU-GPU connection that they feel is bottlenecked. In iGibson's case, I have not heard directly from them, but my sense is that they are using PyBullet separately from PyRender to combine rendering and physics. In Habitat 2.0 case, we have a fairly tight integration between our renderer and our physics engine. So our physics engine is actually aware of the rendering, and the rendering is aware of the physics. And so when objects go out of view or when objects are asleep, we are using that information across these two, across rendering and physics. We also have a couple of tricks like physics is happening on the CPU and rendering is happening on the GPU. And there are a couple of tricks like trying to break the dependency between the two so that the two can happen in parallel. We will put out a paper in a few weeks, a draft of our work. And so I encourage you to look at that for more details.
Yeah, thank you for your answer. So I'd like to know if there are any further questions from the audience. Yeah, it seems. So I actually have a new question. So yeah, also I posed this question to Roosberg, who's talking about AI tour simulators previously. So actually, we are working on it in a simulated world for this kind of embodied AI. I'm just curious that if we want to move to the real world. So Roosberg also in AI2 also mentioned that there are some domain gap, and also there can be some issues that lacking ground truths for training like that. So what kind of issues do you foresee when we move to real world, and also do you think it's worthwhile to kind of have one step further to think about embodying AI in the real world things?
Sure. So I think it's important to test this generalization. And in prior work, we have done this test for navigation. We have not done sim to real tests for mobile manipulation yet. I suspect they will happen in the future. But I'll sort of make a couple of claims. To me, this plot is much more important than the fact that one of the points does not go to 100. So what is this plot? On the x-axis, so every point is a method. On the x-axis is its performance in simulation. On the y-axis is its performance in a real environment. And this is a parallel environment. So we have scanned that same space, we have loaded the same robot and so on. And so then when you get close to the y equals x line, what's happening is that you are confident that the number you're seeing in simulation is predictive of the number you will see in reality. To me, this is much more important than trying to get 100% if you want to use your simulation as a stand-in for reality. If all you want to do is use simulation data to train, and you're not going to do zero-shot adaptation, you're going to do adaptation with real data as well, then this is not that important. The way I think about simulators is that they are good iteration cycles. They let you evaluate your idea. I am not aware of a single idea that only works in reality, that just simply does not work in simulation. And that tells me that we have to get the experiment time down in simulation. Your ideas have to survive in simulation, and then we can test them on reality. And I think of simulation is fundamentally no different than reporting results on a data set like COCO or Pascal or ImageNet. That does not mean when you report a result on COCO or Pascal or ImageNet, you are not making a claim that it will work on your phone or it will work on a self-driving car. You're just making a claim that this is a benchmark. We can measure systematic progress. Things are, correlated with these things that are downstream.
I think that's a good answer. Yeah, thank you. Okay. Yeah, so I think this is the end for our workshop. And thank you all for coming, and thank you for the audience, and also thank you for our invited speakers. Yeah. And so, yeah, Suyan, would you like to say something before we leave?
It's 7 a.m. on my side, so I'm kind of. But I was thank Shuhang for the wonderful organization and speech, and thank you all the organizers and speakers for the incredible talk. And I think we are still going to go for next year. So if we have any progress or if we have any further talks, welcome to our workshop for next year. And yeah, we'll see you next year. Thanks.
Yeah, thank you. I'll see you next year. Yeah.
Thank you for organizing this.
Yeah, thank you. Okay.
Thank you.
So maybe we can call it a day.